everyone, welcome to CAIE Science, and today we will be solving May-June 2022 variant 4.1 of 9701. Basically, variant 4.1 and variant 4.3 are the same. Okay, so the both variants are the same. Okay, so let's begin. Question number 1: the solubility of groups 2 sulfates decrease down the group. Explain why. The solubility decrease because the lattice and hydration enthalpy decrease down the group. Okay, the lattice and enthalpy and hydration enthalpy decrease down the group. And why the decrease? Because down the group because because ion charge density decreases down the group. Okay, and hydration enthalpy decreases more. The hydration enthalpy decreases more. So the solution enthalpy change of solution. So enthalpy change of solution is less exothermic, or you can say less negative. Okay, so that's why the solubility of group 2 sulfates decrease down the group. Okay, and the equation for this relation between enthalpy change of solution and enthalpy change of hydration and lattice enthalpy is enthalpy change of solution is equal to enthalpy change of hydration minus enthalpy change of lattice enthalpy. Okay, from the equation, if the hydration enthalpy is decreasing more, then this will be negative, and this enthalpy change, lattice enthalpy, sorry, is also negative. So this is going to be positive and this is going to be negative. And if hydration enthalpy is decreasing more and the negative value is increasing, so overall this enthalpy change of solution is going to be negative, sorry, less negative. Okay, less negative. Okay, so the enthalpy change of solution is going to decrease. Part B: describe what is observed when magnesium and barium are reacted separately with excess of dilute sulfuric acid. When metals are reacted with acid, they form salt and hydrogen gas. Okay, so due to hydrogen gas, you will going to observe fizzing in both of the reactions. Okay, fizzing. Okay, and the other observation is going to be with barium. When barium reacts with sulfuric acid, it will form barium sulfate, and barium sulfate is insoluble. So you will also get a white ppt, because this is group 2 salt, metal salt, so this is not going to be colored salt and this is going to be a white solid. Okay, white precipitate is going to be formed. So fizzing and white solid. Okay, you will observe white solid forms. And in magnesium you can also write that the solid dissolves, the magnesium dissolves. Okay, you can write that. Part C: the solubility product Ksp of barium sulfate is 1.08 into 10 to the power minus 10 mole per dm minus 6 at 298 Kelvin. Okay, calculate the solubility of barium sulfate in gram per 100 cm cube solution. Okay, so the formula for the equation for the solubility of barium sulfate is like this. And barium sulfate is soluble, or suppose, then it will form barium 2 plus ions and sulfate 2 minus ions. Okay, so it will going to be uh, the ions in the solution. This will have these ions. Okay, and if, let's suppose, the concentration of barium is x, so x moles of barium 2 plus ions will form and x moles of sulfate ions will form. Okay, and the formula for the ksp is equals to concentration of product of concentrations of ions of sparingly soluble salt. Okay, so this is the formula for the ksp of barium sulfate. Okay, and it has given you the value of ksp, which is 1.08 into 10 to power minus 10. Okay, 1.08 into 10 to power minus 10. Okay, and then if we consider the concentration of barium as x, and so this is going to be x square. Okay, so from here you will find x, and x is going to be 1.04 into 10 to power minus 10. Okay, and this is in mole per dm cube. This is the concentration of barium sulfate in mole per dm cube. Okay, but you want the solubility of in gram per, so okay, so you want in gram per cm cube. Okay, so to change it into gram, you have to multiply it with its mr of barium sulfate, because number of moles is equals to mass divided by mr or ar. So mass is equals to number of moles multiplied by ar or mr. Okay, so let's continue here. 1.04 into 10 to power minus 4 multiplied by the mass of barium sulfate. You will calculate from periodic table. It is going to be 233.4. Okay, and then you have to also change the dm cube into cm cube. But remember, the 1 dm cube is equals to 1000 cm cube. So 100 cm cube is going to be how many dm cube? So by cross multiplication you will get x is equals to 0.1 dm cube. Okay, so this and this 0.1 is equals to 1.10. Okay, so from here to see that you have to divide it by 10. Okay, so to change into cm cube, 100 cm cube. Okay, so and from there you will get the answer in gram per 100 cm cube of solution. Okay, and that's going to be 2.43 into 10 to power minus 10. Okay, this is the answer, final answer, 2.43 into 10 to power minus 4. Okay, moving towards next part, part D. The equation for the formation of gaseous sulfate ion is shown. Okay, calculate the standard enthalpy change of formation of sulfate. Okay, this is the formation enthalpy change of formation of sulfate. Okay, it may be helpful to draw a labeled diagram energy cycle. Labeled energy cycle. Okay, use the relevant data from table 1.1 in your calculation. So you can't directly calculate the enthalpy change of formation of sulfate. Okay, so you have to construct a cycle. So let's say, what is the enthalpy change of barium sulfate? You are given enthalpy change of barium sulfate. So if I write here barium sulfate, so enthalpy, in the definition of enthalpy change is the formation of 1 mole of a compound from its gaseous ions. Okay, so gaseous ions, so barium sulfate, ions of barium 2 plus sulfate, and this is in gaseous form. Okay, then the sulfate ions in gaseous form, they form barium sulfate. So this is the enthalpy, lattice energy of barium sulfate, and its value is minus 2469. Okay, then what is the standard enthalpy change of formation? Okay, formation, if you remember the definition of enthalpy change of formation, it is the formation of 1 mole of an compound from its elements in standard states. Okay, so in a standard state, barium is solid, thus sulfur, which is sulfur is also solid, plus oxygen, okay, which is a gas. These are elements, they form barium sulfate, and this is the enthalpy change of formation of barium sulfate. Okay, and it has a value of negative 1473. Okay, now moving forward, now you have to change this barium solid to gaseous barium 2 plus ion. So firstly, to change it into a solid, you have to change it to gaseous state. So firstly, we will change barium into gaseous state. Okay, so to change into gaseous state, this is called the enthalpy change of atomization. Okay, when 1 mole of atom is found from its elements. Okay, so enthalpy change of atomization of barium is 180 plus 180. So this is plus 180. Then you have first ionization energy. This will change into barium plus 1. Okay, then the second ionization energy. Okay, so the first ionization energy of barium is 50 plus 503. Okay, 503, and the second ionization energy of barium is plus 965. Okay, now to change this, and this is the enthalpy change of sulfate ions. Okay, you are given here, this is the enthalpy change of formation of sulfate ion, and this is what you have to calculate. I am writing this as x. Okay, so now the cycle is completed, so you have to just write it here. Okay, see the arrow which are head to tail. Okay, so this goes like this, the cycle, and then it's like this. So this part is going to be on the one side, and this part is going to be on the other side. Okay, so 180 plus 503 plus 965 minus 2469 plus x is equals to minus 1473. Okay, so from here you will calculate the value of x, and x is going to be negative 652. Okay, so this is your answer. This is the enthalpy change of formation of sulfate ion. Okay, Moving towards next part, suggest how the lattice energy of barium sulfate differs from the lattice energy of CS2 sulfate. And this is you see here, this is calcium. Okay, this is calcium. Okay, so the lattice energy, how suggest how the lattice energy of barium sulfate differs from the lattice energy of calcium sulfate. Okay, explain your answer. So from the periodic table, we see that the barium sulfate, barium and calcium are in same period. Okay, but you can see that the across the period the ionic radius decreases because the charge, nuclear charge increases, and there is a constant shielding factor because the shell is same. So the charge density of barium is high. Okay, that's why barium will have a more negative lattice enthalpy. Okay, because why? Because the barium has more charge density. Okay, and it is smaller, so there are going to be stronger forces of attraction between ions. Okay, so what is the reason? Barium sulfate is more negative. Okay, because barium 2 plus is smaller. Okay, because it's smaller, so it has a high charge density, so stronger forces of attractions between ions. Okay, between ions. Part E, the reaction of solid hydride barium hydroxide with ammonium salts is endothermic. Okay, calculate the minimum temperature at which the reaction of barium hydroxide with ammonium nitrate becomes feasible to all of your working. You are giving enthalpy change of reaction and the change in entropy. Okay, entropy change. So the relation which connects these two, enthalpy change of reaction and the enthalpy change in entropy, so it's Gibbs free energy. This is the formula for the Gibbs free energy, and when the Gibbs free energy is negative, the solution is feasible. So uh, so you have to calculate the temperature, so we will put this Gibbs free energy as 0. Okay, and the enthalpy change of this reaction is given to you, which is 132 minus, you have to calculate the temperature, and then this is enthalpy, the change in entropy, but you have to calculate it in divided by 1000 because this is in joule and this is in kilojoule. Okay, so to convert it into kilojoules, you have to divide it by 1000. Okay, so let's uh, shift this all negative sign to the other side. Okay, so this is going to be T is equals to 616 divided by 1000 is equals to 132. Okay, so from here you will calculate the value of T, which is going to be 2143.214.3 in Kelvin, but you have to give answer in degree Celsius. Okay, so you will divide this value with negative subtract this value from 273. Okay, so T is equals to minus 273. Okay, so from here you will get the answer negative of 58.7. Okay, degree Celsius. So this is the minimum temperature at which the reaction is feasible. Okay. Moving towards next part, barium hydroxide reacts readily with ammonium chloride on mixing at room temperature. Okay. The enthalpy change of reaction for this particular reaction is given to you. Some relevant standard entropies are given in table 1.2. We calculate the Gibbs free energy for this reaction at 25. So for Gibbs free energy, the you can see from here that the entropy is in Kelvin. Okay, so you firstly convert this degree Celsius temperature into Kelvin. Okay, so this is going to be 25 plus 273, which is going to be 298 Kelvin. Okay? Now the formula for the Gibbs free energy is the same which I wrote above. Gibbs free energy is equals to enthalpy change of reaction negative minus temperature multiplied by entropy change. Now you are giving temperature and enthalpy change, but you have to calculate the entropy change, and the formula for the entropy change is equals to entropy of products minus entropy of reactants. Okay, and you are given the entropies of products and reactants in the table 1.2. Okay, so from there the entropy of products is this entropy of these substances. Okay, so ammonia, barium chloride, hydrated barium chloride, and water. Okay, there are 2 moles of ammonia, 2 multiplied by 92, plus barium chloride, which is has an entropy of 203, plus water has an entropy of 70, and there are 8 moles of water. Okay, minus we have the barium hydrated barium hydroxide. So, okay, so it has an entropy of 427, plus ammonium chloride, it has an entropy of 95 and it has 2 moles. Okay, so from here you will get the value of entropy change. Okay, and this is going to be 530. Okay, 530. Okay, so now you know the value of entropy change and the value of enthalpy change, and yet the temperature is also given. So the Gibbs free energy is going to be 133 minus 298 multiplied by 530 divided by 1000, because this is in joule per Kelvin per mole. Okay, so you have to convert it into kilojoules. Okay, so from here you will get the value of Gibbs free energy, which is negative of 24.9. Okay, so this is the answer. I hope you understand that. Okay, question number 2, part A, define transition element. Okay, so transition elements are the elements which form one or more stable ions with incomplete or partially filled d orbitals. Okay, so elements which form one or more stable ions with incomplete d orbital. Okay, d orbitals. Okay, this is the definition of transition elements. You have to remember that. Part B, sketch the shape of dz square orbital. Okay, so the shape of dz square orbital, you have to remember that. Okay, so it's like this. Z, you have to be on the z axis. Okay, okay, and then this is like this. So this is the shape of dz z square orbital. Okay, part C, manganese 4 oxide MnO2 acts as a heterogeneous catalyst in the decomposition of hydrogen peroxide. Okay, what is meant by a heterogeneous catalyst? A heterogeneous catalyst is a catalyst which is in on the different state or phase to the reactants. Okay, the catalyst and reactants are in different phase. Okay, describe the mode of action of heterogeneous catalyst. So in the heterogeneous catalyst, the catalyst is usually like solid and reactants are in gases, for let's suppose. So the reactants are absorbed on the surface of reactant on the surface of catalyst. Sorry, reactants are adsorbed on the surface of catalyst, and then the bonds in the reactants are weakened and new bonds are formed, which are then dissolved. Okay, so the mode of action is, there is adsorption of reactants to the surface of catalyst. Okay, and bonds in reactant are weakened. Okay, bonds in reactants weakens. Okay, and new bonds are formed. Okay, and reaction occurs. And the products are dissolved. Okay, and products are dissolved. Okay, so this is the mode of action of heterogeneous catalyst, which you have to remember. Okay, moving towards next part D, manganese 7 oxide Mn2O7 can be made by treatment of KMnO4 with concentrated sulfuric acid. Okay, this is reaction 1. Okay, then manganese 7,4 Mn2O7 readily decomposes at room temperature to form manganese 4 oxide and a colorless diatomic gas. So this manganese 4 oxide is a formula of MnO2. Okay, and this is the reaction 2. Okay, so construct equations for the both reactions described. Okay, so for the first reaction, which is the Mn2O7 is formed when KMnO4 potassium manganese 7 reacts with concentrated sulfuric acid. Okay, so this forms manganese 7 oxide. Okay, plus it will form the sulfate ions, and potassium ion will react to form potassium sulfate. Okay, and then there is also hydrogen and oxygen, so it will form water. Okay, like this. So you have to balance the equation. So this is the equation for the reaction 1. And by the way, here you can also write this, that this can form potassium hydrogen sulfate. Okay, this can also be formed. So this can also be formed. Okay, but this equation is also correct. Okay, and for this reaction 2, the Mn2O7 readily decompose, okay, to form manganese oxide plus a diatomic gas, which is going to be oxygen. Okay, oxygen. And now you have to just balance the equation. So this is going to be like this. Okay, this is the balance. Okay, moving towards next part, part E. Aqueous manganese 2 ions show similar chemical properties aqueous copper 2 ions when reacted separately with sodium hydroxide and concentrated HCl. Okay, write the ionic equation and state the type of reaction for the reaction of manganese complex with sodium hydroxide. Okay, the ionic equation. Okay, so for this ionic equation, the manganese complex H2O6 reacts with OH ions. This will react with OH ions. Okay, and the OH ions will displace these some of water molecules, okay, from the complex. Okay, and this will form manganese OH 2. Two of the OH groups will displace two of the water molecules. Okay, so this will form manganese complex like this, and this will have no overall charge because hydroxide then have a ion charge of -1, and there are two hydroxides, so this will have a charge of -2 in overall, and there is no charge on water, and manganese has a charge of 2 plus from this complex. Okay, so this will balance the charge. Okay, so this will be the complex plus, and it will form also water. Okay, the water which was eliminated. Okay, now you have to balance the equation. So this type of reaction is acid base reaction or precipitation reaction. Okay, so this is acid base reaction. Acid base reaction. Here water is acting as a base. Okay, now moving towards next part. Okay, write the ionic equation and state the type of reaction for the reaction of manganese, this complex of manganese with concentrated HCl. Okay, so when this will react, and you have to remember that the reactions are similar to that of with copper ions. Okay, so you have to remember the reactions of sodium hydroxide and concentrated HCl with copper ions. Okay, 2 plus plus Cl minus, so this will form MnCl4. The geometry of this complex will be changed because the chloride ions are larger molecules, larger. Okay, chloride ions are larger, so they will not form 6 bonds. Okay, they will form 4 bonds, and the sign of this complex will be changed to -2 because the chloride ion has a charge of -1, and there are 4 chlorides, so this will be 4 minus, and the manganese has overall charge of 2 plus. Okay, so the overall charge is -2 plus the water molecules, and there are 4 chlorides. Okay, so this is the ligand exchange reaction. Okay, ligand exchange reaction. Okay, or you can call it as a substitution reaction. Okay, part 3. The table 2.1 lists relevant electrode potentials for some electrode reactions. Okay, suggests the formula of manganese species formed when manganese 2 plus reacts with chlorine. Okay, so this is chlorine, and which manganese 2 plus. Okay, manganese 2 plus is reacting. Okay, so if you see here, the type of reaction, formula of manganese species formed, and type of reaction. So which manganese species will react? Okay, so Mn2 plus is reacting. Okay, so this equation has Mn2 plus. Okay, and if and you can see that this has a high electrode potential, so this is going to reduce. Okay, because these are giving reduction potential, and this is has low reduction potential. Okay, so this is going to oxidize. Okay, so the overall equation is going to be 2 plus chlorine, this form chloride ions, and Mn2 plus water, this forms manganese 4 oxide plus 4H plus 2 electron. So which manganese species is formed? This is manganese 4 oxide, or MnO2. And what type of reaction is this? This is a redox reaction. Okay, because the chlorine is reduced and Mn2 plus is oxidized to Mn4 plus. Okay, question number 3. The rate of reaction between 2-chloro-2-methyl propane. If I draw this structure, this is going to be sorry 2-chloro-2-methyl propane. Okay, CH3. CH3. Okay, this is the structure of 2-chloro-2-methyl propane, and methanol is investigated. A large excess of methanol is used. The overall reaction is first order. Okay, the large excess of methanol is used, so it will have no effect on the rate, because this is going to be in the can say this is going to be a zero order reaction. The order of the reaction with respect to methanol is going to be a 0, and the overall reaction is first order. Okay, the equation is given to you, and figure 3.1 shows the results obtained. Okay, use the graph to determine the rate of reaction at 40 seconds. So here's something here, 40 seconds. Okay, so on 40 seconds you have to draw a tangent. Okay, like this, tangent to the curve. Okay, I have no scale here, so but you have to draw accurately. Okay, and then you have to calculate the gradient of that tangent. Okay, so to then you have to just calculate the gradient of this tangent. Just took 2 points from this line, and then just calculate the gradient, and this gradient is going to be 0.00 0.0170. Okay, I'm not calculating here, but I have given you a hint that how you will calculate the rate of reaction at 40 seconds. Okay, you have to just draw a tangent and then calculate the gradient of this tangent, or slope. You can say slope of this tangent. Okay, moving towards next part. Use the graph to show that the overall reaction is first order. Okay, so for the first order, the half-life is going to be constant. Okay, the half-life of the first order reaction is constant. So if you see, what is the initial concentration of 2-chloro 2-methyl propane? Okay, which this is 0.02. Okay, and then by just is this, then this to half. What is the half of this? 0.01. This is 0.01. Half of 0.02 is 0.01. And let's see what is the time here. This is the half-life, first half-life. Okay, and this is approximately like this, and this is approximately like 30. Okay, then calculate the second half-life. So second half-life is going to be like this, and this is something like this here. This is approximately 60. Then if you want to calculate the third half-life, you can calculate just half this 0.05. You will get 0.025. Okay, and you will get it 90, approximately 90. Okay, so you can see the first half-life is 30, then 60, second half-life, and then 90. So the half-lives are constant. Okay, there is a half-life is 30 degrees Celsius. Oh, sorry, 30 seconds. Okay, the half-life is 30 seconds. Okay, so there is a constant half-life. So there is constant half-lives. Okay, half-life, there is constant half-life. Okay, so this is going to be the first order reaction. Moving towards next part B. In a different reaction, which is also a first order reaction, 75% of the reactant is consumed in 320 seconds. Calculate the rate constant K for this reaction. Okay, state the unit of K. Now this was a little tricky because this told you that the order of the reaction is first order. Okay, and this means that the half-life is going to be constant half-life. Okay, the first order is telling you this, and then 75% is consumed. So for the first half-life, if you see, let's imagine that 100% was the original uh, the original the concentration. Okay, so on the half-life, on the first half-life, this is going to be 50%. Okay, and then on the second half-life, this is going to be half of this, and which is going to be 25%. Okay, so 75% is used up. Okay, and this is also telling you this, the 75% of the reactant is consumed. Okay, in 320 seconds. Okay, so on the two half-lives of the first order reaction, the 75% of the reactant is consumed. Okay, so what is going to be the half-life? So the half-life is going to be, there are two half-lives. The two half-lives are, you can say, two half-lives are involved. Okay, so there are two half-lives. So the half-life of this reaction is going to be 160. Okay, there are two half-lives which involved, which makes the 75% of the reactant to be consumed. Okay, so the half-life of this reaction is going to be 160. 160, sorry. And the formula for the first half-life, the reaction is formula for the first half-life is ln2 by uh, k, ln2 by k, sorry. And this ln2 is going to be 0.693 in upon k. Okay, so from here you can calculate the value of k, which is going to be 0.693 divided by half-life, and the half-life is going to be 160. Okay, so from here you will get the value of k, which is 0.00433. Okay, and the units are going to be second minus, okay, minus 1, 0.00433. Moving towards next part, part C. Define a standard electrode potential. Okay, what is the standard electrode potential? This is the voltage when half cell is connected with a standard hydrogen electrode under the standard conditions. Okay, voltage when a half cell, when a half cell is connected to standard hydrogen electrode under standard condition, under standard conditions. Okay, so this is the definition of electrode, standard electrode potential. Okay, a salt bridge is used in an electrochemical cell. Okay, state the function of salt bridge. Salt bridge. So the salt bridge let the movement of ions and prevent the salt bridge actually transfers or moves ions to maintain the charge. Okay, charge balance. Okay, so ions move from salt bridge to maintain charge balance. Okay, part 3. Complete the diagram of the apparatus that can be used to measure the electrode potential of the chromium 7. Okay, dichromate 7 ion. Okay, and okay, this electrode. Okay, against the standard hydrogen electrode. Okay, you have to draw a diagram to show how to measure the electrode potential of this dichromate, this electrode against a standard hydrogen electrode. Okay, so first thing you have to remember that the electrode potential of the hydrogen electrode is 0.00. Okay, that's why this is the standard electrode. Okay, your diagram should be fully labeled to identify all apparatus, substances, and conditions. Okay, so firstly, let's make the hydrogen electrode. Okay, firstly I'm making hydrogen electrode. So hydrogen is a gas and this electrode is of platinum. Okay, platinum, and the hydrogen is inserted from here. Okay, hydrogen gas. So this is the platinum, and the second electrode, this is also not in solid form, it is in aqueous form, so we will use a platinum plate. Why platinum is used? Because this is inert. Okay, you know that platinum solid, this is platinum solid. Okay, so this combines to give a voltage. Okay, and this is the solution. The salt bridge is also dissolved between two solutions. Okay, and in this solution you have, for how many ions? Okay, you have chromate, dichromate, 7 ions, aqueous, and H plus aqueous, and chromium 3 plus aqueous ions. Okay, these are the ions present in this electrode, and there are only H plus ions present. Okay, and what are the standard conditions? This also told you that include also standard conditions. Okay, so the standard conditions are room temperature but in Kelvin. Okay, and 1 atm pressure and 1 mole per dm cube of concentration. Okay, these are the standard conditions of the to measure the standard electrode potential of any cell. Okay, half cell. So this is your label diagram. Okay, part 4, the electrode potential of the dichromate 7 electrode is positive 1.33. so this means this is reduced. Okay, because the electrode potential of hydrogen is 0.00, so this is the less electrode potential, the hydrogen is oxidized and this is reduced. Label the negative electrode and the direction of electron flow in the external circuit when the electron flows in your diagram. Okay, so this is a reduction. So reduction happens at cathode, so which means this dichromate 7 electrode is cathode, and in this cell the cathode is positive because anode is where the electrons are uh, generated. Okay, electron flow starts. Okay, electrons flow from positive, okay, sorry, anode. Okay, electrons flow from anode. Okay, and anode is hydrogen. Okay, so anode is going to be negative electrode, so this electrode here is going to be the negative electrode and this is going to be the positive electrode. Okay, and the direction of electron flow is from hydrogen to dichromate electrode. Okay, and this negative means anode and positive means cathode. Okay, this anode shows that there is oxidation and cathode shows that there is reduction, and this negative sign shows that the electron flow is from anode to cathode. Okay, moving towards next part D. Table 3.1 lists relevant electrode potentials for some electrode reactions for use in D1 and D2. Okay, the table 3.1 gives you the electrode reactions and electrode potentials of some of the electrode reactions. Okay, part 1. Ethanol is oxidized to ethanoic acid. This is the equation, ethanol. And by the way, in these electrode reactions, you are given reduction potentials. Okay, in the presence of chromate, dichromate ions. Okay, construct an ionic equation for the oxidation of ethanol to ethanoic acid using dichromate 7 in acidic conditions. Calculate the E cell for this reaction. Standard electrode cell. Okay, standard cell potential. Sorry. So dichromate ion, okay, you can see from here that the dichromate ions have greater reduction potential, so this is going to be reduced and this is going to oxidize. So, and for the oxidation we flip the equation, okay, ethanol CH3 CHO plus H2O, this becomes ethanoic acid plus 2H plus 2 electrons, okay, and we have then dichromate 2 minus plus 14H plus 6 electrons. So where here we will multiply it with 3, okay, so to balance the electrons, okay, there are 6 electrons. To balance the electrons we have to multiply by 3, so to make it 6 electrons, okay, because in the ionic equation we have to cancel out the electrons. This becomes 2 chromate 3 plus 7 moles of water, okay. Now here you will after multiplying it with 3 you will cancel out the electrons, so what are you left with, okay, so this is 3 moles of ethanol plus, and water, there are 3 moles of water here and 7 moles of water. So if you uh, take these 3 moles of water to on the right hand side, you will have a negative sign and this will be a 4, okay, 4 moles of water here, 4 moles of water here, and there are 14 H plus ions on this side, left side, and after multiplying it with 3 you will have 6 moles of H plus ions on the right hand side. So there are going to be 8 moles of hydrogen after subtraction, okay, and then chromium 3 plus ethanoic acid CH3CHCOH plus, then there are going to be 4 mole of H hydrogen water, sorry. And what is going to be the E cell? E cell has E reduction minus A oxidation. So what is the reduction potential which is reduced, okay, so reduction potential is 1.33, okay, and what is the oxidation, which is negative 0.94, okay, so in total this is going to be plus 2.27, okay. Moving towards next part, in an ethanol oxygen fuel cell, ethanol and oxygen are in contact with two inert electrodes immersed in an acidic solution. The cell reaction for the oxidation of ethanol by oxygen is shown. Okay, ethanol is oxidized to ethanoic acid. The E cell for this reaction is shown. Calculate the Gibbs free energy for the oxidation of ethanol. Okay, so the formula for the Gibbs free energy, and this is the second formula, which is negative of N, where N is moles of electron, F, which is Faraday constant, and E cell. Okay, E cell is given to you. Faraday constant, we know its value, which is 96500. Okay, and now you have just to find the value number of moles of electrons which are transferred. Okay, so you can see from the oxygen electrode, this is, there are 4 electrons transferred, okay, and you can also see from ethanol is oxidized to ethanoic acid. So first it will be oxidized to ethanol, Then ethanol is oxidized to ethanoic acid. Okay, so there are also 4 moles of electrons transferred. Okay, when you will multiply it by 2. Okay, so negative of 4 multiplied by 96500 multiplied by E cell, which is 2.01. Okay, so from here you will get a value of negative 77586. And here you have to remember that the Gibbs free energy is in joule per mole. Okay, not in kilojoules per mole, joules per mole. So you have to convert it into kilojoules per mole. So divided by 1000, you will get 776. Okay, 776, 776. Okay, moving towards next question. Question number 4. Part A, the 3d orbitals in an isolated Fe2 plus are degenerate. Okay, degenerate means of same energy level. Okay, complete the diagram to show the splitting of 3d orbital energy levels in an isolated iron 2 plus ion, and when iron 2 plus ion forms an octahedral complex. So in octahedral complex there is a d-splitting. Okay, and in octahedral the splitting is in a different way to the splitting in tetrahedral complex. Okay, I will show you. So let's do this one. So how many orbitals are there in d subshells? Okay, sorry, there are 5, 4 and 5, like this. So here this is dxy, dyz, dxz, and you have then dx square minus y square, then there is dz square. Okay, and how many electrons are there in iron? Okay, Fe2 plus. If you see from the periodic table, this is iron, and iron has 26 protons. Okay, you can see from here that iron has 26 protons. Okay, so which means this is iron 2 plus ion, so it will have a 24 electrons. Okay, 2 electrons are lost. Okay, and then if you write the electronic configuration of this iron 2 plus, let's write it here. Iron 2 plus, this is going to be 1s2, 2s2, 2p6, 3s2, and then there is 3s2, 3p6, 4s2. So how many electrons are there? 10 and 10, 20. Then you have 3d4. Okay, okay, I'm sorry, we have, sorry, not 4s2. Okay, you have 3d6. Okay, okay, so that's right. Now you have 3d6 and you are dealing with the 3d orbital. Okay, so here now firstly just write the electronic configuration of iron. Okay, so firstly I am writing of just of iron, Fe iron. Okay, iron atom. Okay, so it's going to be 4s2 and 3d6. Okay, then of iron 2 plus, this is going to be a 4s0 and 3d6. Now that's right, okay, because the 4s is above the 3d, so this is going to be the valence shell, okay, and electrons are removed from 4s, okay. So there are 6 electrons in 3d and we have to arrange them. So 1 2, first there will be all unpaired of electrons, 5, and then the sixth one here, okay. This is the uh, electronic structure, okay, of the in the isolated iron 2 plus, okay. And when there is it forms complex, it splits into two portions, okay, of higher energy level and lower energy level, okay. In lower energy level, in octahedral complex, we have dxy, dyz, and dxz, okay. And in upper energy level, higher energy level, we have dx square minus y square and dz square, okay. Now from in in which way we arrange the electrons, we start from the lower energy level, okay. Electrons start to enter from lower energy level, so 1 2 and 3, okay. You have 6 electrons, right? So 1 2 3 and then 4 5 and 6, okay. So there are no electrons in higher energy level, okay. So this is the uh, splitting pattern and how electrons are arranged. You have to uh, be familiar with that, okay. Part B, a bipyridine is a bidentate ligand, okay. Explain what is meant by bidentate ligand, okay. So it's a ligand or a species that donates two lone pairs to central metal ion to form dative bonds to the central metal ion, okay. Species which donate two lone pairs is called a bidentate ligand, okay. The complex b pi exists as a two stereoisomerism, I'll complete the three-dimensional diagrams to show the two stereoisomerism of iron bipi 3, okay. It's the type of stereoisomerism shown, okay. Use this symbol to represent the bipi in your diagrams, okay. So bipi is a bidentate ligand, so it donates two lone pairs, okay. So there are three bipi, so it forms an octahedral complex, okay. It will donate 6 lone pairs, so it will form an octahedral complex. So octahedral complex, we will draw it like this. So firstly we have n, we have to show the bipi bond with this symbol, okay. So this is like this, and then other is going to be a non-superimposable image of, they are going to be non-superimposable images of each other, okay. So this is going to be like this. So what type of isomerism is shown? It is optical isomerism. Okay, they are non-superimposable images of each other. Okay, you can see that. Part C. Standard electrode potentials can be used to compare the stability of different complex ions for a given transition element. Table 4.1 lists electrode potentials for some electrode reactions of iron 3 plus and iron 2 plus system. Use relevant data from table 4.1 to state which iron 3 complex is hardest to reduce. Then your answer. So I told you earlier that in electrode reactions you are given reduction potentials. Okay, so one with the lower reduction potential is hardest to reduce. So here you can see that this complex has a lower reducing potential. Okay, so this is going to be hardest complex. This is going to be a complex which is hardest to reduce. Okay, so Fe and 6 P minus. Okay, and what is the reason? Because it has lowest E node value. Okay, moving towards next part D. Okay, the ligand bipyridine consists of two pyridine rings. Okay, pyridine and benzene have similar planar cyclic structures. Okay, by reference to the hybridization of carbon atoms and nitrogen atom and orbital overlap suggests how sigma bonds and pi bonds are found in pyridine. Okay, so this structure of pyridine is similar to that of benzene, and in benzene each carbon has a hybridization of sp2. Okay, and nitrogen, here it will have also hybridization of 2 plus sp2. Okay, because it forms three bonds, so sp2 hybridization of Na2. So what will you write? There is sp2 hybridization of nitrogen and carbon. Okay, and sigma, how sigma bonds are formed? Sigma bonds are formed by overlap, end-to-end overlap between ss sp orbitals. Okay, and how pi bonds are formed? They are formed by sideways overlap of p orbitals. Okay, so sigma bonds are formed by head on overlap orbitals between head on overlap between orbitals. Oh, sorry, head on overlap orbitals between you can see between carbon double bond. So carbon bond. Okay, carbon bond, and there is also a single bond in pH. Okay, there is an overlap, head on overlap between sorry, this is in pi bond. Okay, okay, there is a head on overlap orbital between CH. Okay, orbital. This is between carbon carbon single bond. Okay, for carbon carbon single bond. Okay, and how pi bonds are formed? Pi bonds are formed. Pi bonds are formed by sideways overlap of of p orbitals. Okay, p orbitals between there is a triple bond in CN and carbon carbon double bonds. Okay, so uh, you can write it as between carbon and carbon bond. Okay, or you can also write it as carbon carbon bond. Okay, moving towards next party. Pyridine reacts with chlorine in the presence of LCl3 as shown in figure 4.3. The mechanism for this reaction is similar to that of chlorination of benzene. Okay, LCl reacts with chlorine to generate a electrophile C plus. Okay, complete the diagram to show the mechanism for the reaction of pyridine with Cl plus. Include all the relevant charges, dipoles, lone pairs of electrons, and curly arrows. Okay, so firstly, this electrophile will be attacked by the nucleophile, which is carbon carbon double bond in pyridine. Okay, so this carbon carbon double bond will attack this electrophile, and then this electrophile will be attached like this. Okay, like this. I'm not good with drawing. Okay, so, and this double bond will be you have to show this like this. Okay, and then this hydrogen will be will donate its electrons to a ring, and this hydrogen will form H plus ion. Okay, so this is the intermediate, and then it will form, sorry, I missed nitrogen. Okay, so this will form 3-chloropyridine plus H plus ion. Okay, so this is the mechanism for the reaction. Okay, I think I am this is all for the day. We will do other questions in a second part, because this is a long paper, and I think video is going to be too long if I this all paper in one video. So let's keep this here, and I will deal with other questions in the next video. So till then, uh, take care of yourselves, and thanks for watching. If you haven't subscribed my YouTube channel, do subscribe. Okay.